Evan Schwab's at Philips. He does explainable AI every day. There'll be some parallels to what happened in our previous talk. Maybe we'll get into some of the packages, hear about that research as well. So give a round of applause for Evan.
Thank you. Thank you very much. Yep, so my name is Evan Schwab. Can everyone hear me all right with this? I work at Philips. I'm a research scientist, and so we are located in Cambridge, Massachusetts. We have a new headquarters there. And so in this talk, I'll be explaining to you my passion about explainable AI. And in the scenario where we have weak annotations, so we don't have all the annotated data that we would like, and so this happens a lot in medical data, and what we can do to circumvent that. So right, the two themes that I'd like to talk more about is weakly annotated data and explainable AI. So first, I'll explain what are annotations, what do I mean by that in machine learning, and then secondly, what do I mean by weak annotations. And then following that, we will look at some of the state-of-the-art for explainable AI and how we can improve upon it and what work we've done at Philips to do that. So the type of data that I look at are images. And this is the realm of computer vision. And so there's many applications of using AI for images, such as self-driving vehicles, robotics, social media, and search engines. And we're interested in analyzing these images automatically using algorithms to try to either detect certain events or objects in an image, to try to segment something, or even to caption an image. For instance, there's a man in a black shirt playing guitar. So that was an automatic caption that was generated given that image. But since we're at a healthcare conference, we're mostly interested in medical images. So that's MRI, CTs, X-rays. And we can do a lot of the same types of tasks where we want to automatically analyze these images by segmentation or object detection that can be used for robotics. We can also do image captioning, you see as well. And what I like to think about are some of the parallels between some of the algorithms that have been used in computer vision for natural images and those that can be applied to medical images. And there are a lot of differences, actually. So right off the bat, so I've done just a simple Google search for cats. Cats seem to be a very hot topic in social media for some reason. And so you can see a lot of different orientations, poses. There's cats that are occluded by something in the foreground. And what we notice that there's no limit of how many cat images we have. So this is great for training machine learning algorithms, especially deep learning algorithms. And as well, we have lots of annotations. You can really crowdsource this type of thing. And anyone can identify a cat. So anyone can trace where the cat is in the image. Anyone can draw a bounding box around the image. And you don't need any type of expertise to understand what a cat is. Now, if we go to medical images, right off the bat, you see something very different. If I Google chest X-ray, they all look the same, basically. So we are constrained by the modality. We are constrained by the anatomy. Most people will have two lungs visible, the same set of bones, and the image will be a grayscale image. And you don't see many different orientations. There's no foreground, background. So at the onset, it seems like it could be an easier problem even, that there's not as much variation to learn. But we have a lot of issues here, as you well know. To acquire that data, we need consent from the patient. We need to worry about de-identification of the data so we can't trace it back to that patient. There's all this privacy. We have limited availability. So not only do we have less images in total, on top of that, we have even less annotations. So to actually annotate these images, we need medical trained experts who have gone through years and years of schooling in order to figure out how to analyze these chest X-rays. And if you were to ask a physician to do that, it's very time consuming, it's very expensive, and you might find a lot of actual disagreement between physicians. It's not an easy task to do because there are very subtle findings. The last difference is one about accuracy. So this is actually a life or death situation when we talk about medical images, as opposed to, for instance, trying to detect a cat in an image. So we need a greater degree of explainability so that we can help the clinicians to understand what the AI algorithm is doing. And we have different levels of accuracy that we need. So back to annotations. What do I mean by annotations? And so this is in the realm of supervised machine learning, where we need some type of ground truth in order to tell how good our algorithm is doing during training. So this can usually come in two forms. One is a bounding box. And this I mean by we can look at the coordinates of that box to define it. And so there's an image of a stop sign, and in green is the ground truth. So that was someone actually manually traced a bounding box around that. And a prediction of an algorithm would be in red. And you can then measure how well the algorithm did by perhaps the overlap of those regions. And the same exact idea can be done with medical images. Then you can go to more of a finer grained annotation, which is in the realm of segmentation, where each pixel in an image has a different class. So there's an image of a street scene here, where cars are denoted by blue, the street is purple, the trees are green. Every single pixel has a class. And our prediction is then on the pixel level prediction. We are going to predict the class of every every pixel. And this is in particular, we have an image, a prostate exam, and also a brain MRI, where sometimes the size of those pathologies matters, and we'd like to measure those. So we don't just want to detect where it is in the image with the bounding box, we actually want to measure it with the number of pixels or the volume or area of that region. So in particular, in this talk, I'll be talking about chest x-rays because they are one of the most frequently administered exams. This is because they're fast, they're non-invasive, they offer low radiation, so they're inexpensive, and they're very versatile. You can look at the heart, lungs, and bones. So it's a very a good first exam to give to a patient that's coming in. And there's a lot of use cases for AI in radiology. As I said, we are interested in detecting critical findings. Other applications are incidental findings, where someone goes into the ER room for a broken rib, but the doctor doesn't notice that that person has lung cancer. We also want to prioritize work lists so we can maybe evenly distribute some of the more severe cases between physicians of different expertise levels. We're also always interested in quality control. And as I said once before, we're also we can estimate or predict the severity of pathology. And between physicians, there's a lot of inter-rater variability between that. And as one of the other themes that has come up earlier in this conference, burnout relief is a big issue. So we can use AI to try to help radiologists to assist them so that they might see less cases, or we can weed out the healthy ones earlier in that case. So in particular, at Philips, we're located right next door to MIT, so we have a partnership with them. And through the Beth Israel Deaconess Medical Center there in Boston, we were able to acquire 350,000 chest x-rays. And so now we're in the realm of big data. But as you saw before, for natural images, that's on the order of millions of images. So it's not yet too big data, but we can still do something reasonable with AI algorithms with that number of images. But the big downside here is that we don't actually have ground truth labels. So we've acquired the images, but we don't have the labels of healthy versus certain disease and such. So how can we go about getting the ground truth to train a supervised machine learning algorithm? One of the popular ways now is knowing that these images come with radiology reports. So that happened during the time of diagnosis. And we can use natural language processing to extract labels from those images, from those reports, so that then we can have labels for the images. So, for example, from these reports, the words mass has come up or nodule has come up. So then these are used as maybe noisy labels to label the image, and we can then use our machine learning with those labels to try to understand the image. But what we don't have from the radiology reports, very specifically, is an indication of where the pathology is in the image. They might say left or right lung, for instance, but to actually extract that information using NLP is a much harder task. So in this case, we have a global label for the image. We have that there's some kind of nodule in the image, but we don't know the local annotation. We don't know where in the image it is. And in this case, this is what I mean by weakly annotated data. So we have a very coarse label, but what we really want is a finer label. And in order to use the out-of-the-box machine learning methods that are able to detect that stop sign, we really need those local bounding box locations of where nodule is in the image. So the goal of my work and the work at Philips is to automatically classify and localize these critical findings in chest X-rays, but without using these local ground truths. And some features that we would like in our design of our network is that it should be explainable so that a clinician could accept the prediction. So if I just told you that there's pneumothorax in this image, that it might not be accepted. A clinician might want to know, okay, where is it in the image? Because I don't know if I trust you. You just told me yes or no, and I would like to know where in the image so I can verify that that's true. Otherwise, we'd also like to design an end-to-end network. And by end-to-end, I mean a single line of optimization. We don't want first to classify it and use that classification to then localize it, because if we got the first step wrong, that could really impact the second step. So that also means we want to do this jointly. We want to jointly classify and localize at the same time. And ideally, it should scale to multiple findings. We don't just care about pneumothorax, we care about all of the ailments that can happen in a chest X-ray. And in theory, this should scale to different modalities, like breast exams that we just saw before. So it shouldn't be so specific to a single modality that that's all we can deal with anymore. And as I said before, we really care about high accuracy, minimizing false positives, false negatives. So the state of the art, and you might have heard of this, is a convolutional neural network. And this is a deep network that has an input and an output. The input is an image, so in this case, a chest X-ray. And for this example, we have a binary classification task. So it's either no finding, so that might be a healthy person, or I use that lightly, it's just you have pneumothorax and no pneumothorax, let's say. And so the output is a score, a probability of having pneumothorax. So in the first part, we see a 0.05, so that's a very low probability of having pneumothorax. In the second case, we see a 0.91, so that's a very high indication of pneumothorax. But that's it. So the CNNs are actually quite good at doing this task. But at the end of the day, all we get is a score that we compare to the label of pneumothorax or no pneumothorax. This doesn't give us any indication of where in the image the pneumothorax is, which I described before would be something a physician might want to know about. So there has been a lot of work, especially recently, on trying to explain the predictions of the CNN. And in particular, these methods are known as saliency methods, where you provide a heat map. And so by heat map, I mean red indicates a high probability that pathology is located there. Blue is a low probability. So from this, you can get a sense of localization. And you kind of got it for free. I didn't use any local labels. All I did was look under the hood of the AI network. And I examined the weights of that network. And then I can see where the network was looking when it made that classification. But there's some couple things that we can improve upon for this type of method. One is, as I said before, I'd like an end-to-end method. This is not done jointly. So first we do the classification, and then we look at the result. So the heat map is not generated during the optimization. So you could correctly classify the image, but get a heat map that really doesn't make sense. The other thing that you might notice is that it's a very coarse heat map. So for that particular image, it's basically highlighting the whole lung region. So that's not actually very informative, I would say, and could actually distract from what's really going on. And there's a reason for this, and I'll get to that right now. So consider like a full resolution chest X-ray, and this is by 1,000 by 1,000 pixels, but usually you can get on the order of 2,000 by 2,000, or even 3,000 by 3,000 pixels. And I want to emphasize that these images will be drawn to scale. So the very first thing that people do when they want to use a CNN, these are usually pre-trained on, let's say, ImageNet, so that they have a certain size that you have to fit your image into before you can put it into the network. And so, for instance, the usual size is maybe around 200 by 200 pixels. So already we've done this downsampling. And as the previous person was alluding to, sometimes when you have very small lesions or small findings, they might actually get downsampled completely out of the image if you were to downsample it in this way. So you might lose completely the details of the pathology that you were looking for in the beginning. The next thing that they do, through the training of the CNN, they output a score for that image. And then what they'll do is they'll analyze the network weights of the very last layer of that network. So here, again, drawn to scale, is a tiny 7 by 7 filter on in this network. And this is the heat maps that they're looking at. And so the heat maps that you end up seeing on the image of your chest X-ray was a upsampling of this tiny little original heat map. So this is why you can see it's very coarse and not very specific to the actual locations. So already there's a few things not advantageous about these types of methods. We're downsampling to begin with, and then we're upsampling this very tiny heat map and get a coarse visualization of what's happening. So instead of that, this motivated us to think about, instead of immediately downsampling your image, why not take a patch of that size and feed that patch into a pre-trained CNN of that size. Then we can similarly generate a heat map using those saliency methods. And now we have a more fine-grained heat map of individual patches of that area. So in this way, we can have a more localized way of viewing some of those pathologies. But the next question is back to our weakly labeled data. We don't have labels for those patches. We don't know which of those patches contains the pneumothorax and which don't. So it begs the question, how do we relate the patches to the original image? How do we relate, how do we compare it against the label of pneumothorax? And so this comes to a paradigm known as MultiInstance Learning. I think the previous person touched upon it briefly as well. But you can think of this as a very toy example. I have 3 keychains, and I have 1 secret room. And I know something about those keychains, but I don't know anything about the keys. So I know that the first set of keys do not open the room, and the other 2 can open the room. So intuitively, as humans, we are able to deduce which key is opening the room. Can anyone identify the green one? Right. So it might be hard to think about how did we come up with that, because it just was so natural. But there's a few ways. One, you could take all of these keys and you know that none of them open the room. So you could see which of those keys are in common with the others. At the same time, you can also look at which keys are in common to these 2 that aren't in common in the other one. So in this way, it's weakly labeled because we have the global label of the keychain, but we don't have the local annotation of which keys are actually doing the work. Analogously, let's think about images. And instead of keychains and keys, let's think about images and patches of that image. So each patch, think of that as a key that opens the room. And basically, one of them is no finding, and the other two are pneumothorax. So we can use AI to see which patches are in common with the one that has no finding, and which patch is more indicative of the actual pathology. And so this is the basis of multi-instance learning, where we break up an image into instances of patches, and we try to relate those instances back to the global label of pneumothorax or no pneumothorax. And so this is the basis of the algorithm that we're presenting, a deep multi-instance learning framework, where again we just divide a full resolution image into a bunch of overlapping patches that are of size appropriate for a pre-trained CNN. And what is output of a CNN is a score. The score is of pneumothorax versus no pneumothorax. And the key to this framework is that we simply take the max score at the end, and that is the patch that coincides, is responsible for the pneumothorax prediction. So at the end, we have both a prediction of pneumothorax or no pneumothorax, and we're also given, we kept track of where that patch came from. So we know which or where that patch is in the image. And just to get you more familiar with how I'm drawing these, so the boxes around each patch are vary from white to red. White is around close to 0. So this one is a white patch. You can see it on the edge here. And then one that's close to 1 is a very thick red patch. So each patch in the image will have a score, and we can visualize it in that kind of weighted way. And so at the end, we can get a coarse localization of where the pathology is in the image. So at Philips, we did a few experiments. The first one was comparing our method to some of the state-of-the-art, like a CNN, and also a segmentation method. So in this case, we're again looking at pneumothorax. And what we do have here is a ground truth segmentation there that was manually done. But for our method, we're not using that during training. The segmentation method has to use that during training. And the CNN doesn't use that during training, but it also doesn't produce a segmentation at the end. And so what we can see is our method is quite comparable to some of the state-of-the-art. It actually does a bit better than the segmentation method and slightly worse than the CNN itself.
Quick question.
Yes?
So when you cut up your images in all these 24 patches, all those are going to get the same global label. So now you're going to have a lot more data samples and a lot of wrong labels. So
Yes. Yep.
So how does the network cope with that?
That's actually the beauty of it, that it does have wrong labels. So it learns to, given a healthy image, all of those labels will actually be correct. So there will be no pneumothorax in that. So from that, we can see what a healthy patch might look like. And we can use that in the rest of the positive, the ones with pneumothorax. So it can weed out the healthy ones and identify the one that was not like the rest, basically. And the other experiment we did, 2 sets of experiments on other data sets where we looked at not pneumothorax, but we looked at pneumonia and pulmonary edema. And so immediately we can see that we can scale from one critical finding to a few critical findings, depending on how much data we have. And it's maybe not optimized, but we get similarly quite good scores of in the 80s for the area under the curves. And I will show you the qualitative results of those. So this is the case of pneumothorax. And to prime you with what you're looking at, you'll see a red blob. That's the ground truth pneumothorax annotation that was manually done. And again, we're not using that at all during our training, but that's just to verify the correctness at the end. And each overlapping patch in an image has a score from 0 to 1. The white, thin patches are close to 0, and the very thick red patches are close to 1. And when we take the score for the entire image, we take the maximum of those patches. So for instance, at the top here, it's 0.99. So that's the score for the image that there is pneumothorax with a probability of 0.99 in this image. And we know exactly where it is. And you can also see that some patches look like they've disappeared, and that's because they're very, very close to zero that you can't even see them anymore. And that's especially the case for a healthy subject here, where all the patches are close to zero, and the maximum patch is about 0.024. So it's not picking up any pneumothorax, and that's correct. So you can see it can very nicely adapt to different types of pneumothorax, different sizes, different shapes. There's even a case where there's 2 spots of pneumothorax, and it can correctly identify both. So it's not limited to a single type of pathology. Next is the case of pneumonia. And it might be a little hard to see, but there's ground truth bounding boxes in blue and green. So here's a green one and a blue one there. And you can see a distinct overlap between the ground truth and our predictions of those boxes. And finally, we have the case of pulmonary edema. And in this data set, this was given to us from MIT, we actually don't have any local ground truth. So there's no bounding box, there's no segmentation to indicate to us if it did well. But we talked to a physician, and he confirmed that it's picking up what it's supposed to. And you can see very consistently that all of the boxes are picking up the lower lung regions. So we can already see that it's doing some consistent findings there. 32. And just in summary then, so we used a method called MultiInstance Learning in order to detect critical findings without local ground truth. And so some features of this, it's a joint classification localization. So this is done end-to-end, and it can be more explainable in that way. It does not require local annotations, which could take months for a medical expert to provide you with. It's an interpretable end-to-end network that I mentioned. We can scale quickly to other critical findings or perhaps unknown abnormalities. And there can be a number of other extensions because it's just based on a CNN. Instead of a CNN, we can do regression, for instance, or multi-class classification, where instead of a yes or no, we could have a severity estimation. And on top of that, as I showed before, we can empower with saliency at the end to provide a very coarse, very fine heat maps on top of it. And as I said before, it's not particular to chest X-ray or pneumothorax, for instance, but we'd like to be able to extend it to other applications or weakly labeled problems. For instance, in 3D, you could think of you have different slices of a 3D CT, for instance, and maybe only one of those slices has the pathology. And so you could use, instead of patches, each slice is a different instance, and you'd like to localize where in the volume the pathology is. So with that, I'd like to say thank you. This is my email at Philips, and this is a rendering of our new headquarters in Cambridge, Massachusetts, right next to MIT, that we'll be moving into the first quarter of next year. Thank you.
Excellent. Okay, and we have a couple minutes for questions. Feel free to raise your hand, and yes.
Have you thought about the multi-label problem? So if you had one image with, say, a lung nodule and pneumothorax occurring at the same time?
Right. So I might consider that like a multi-class problem where we could predict, yeah, so each patch you could, instead of a binary problem, you could have multiple classes. So one patch could indicate the nodule, one patch could indicate something else that you're interested in. And you would have, instead of one score, you would have a vector of scores for each patch. So I think you could think about it in that kind of way.
I'll just go for it. Yeah. Are you using this in the wild right now, and are you seeing anything like as far as anomalous things coming in where somebody has like an implantable device or is that surgery or something like that, just how is it being used in the wild, if at all?
Right. It's not yet being used in the wild, for instance, but we did have a case sometimes with these data sets, because they're taken after someone's diagnosed, they might already have an implant or some kind of tool that was used to fix that problem. And so we actually, early on when training the algorithm, we came across that, that there were medical devices that might be thwarting it. But it was able to understand that those weren't indicative of the disease. So it was able to learn past that. So yeah, and otherwise in the wild, we weren't sure how well it would do with multiple regions of something, and it turns out that it was able to predict those multiple regions of a class.
So you transfer learned through the ImageNet.
Mm-hmm.
Did you modify the architecture of the original ImageNet as well?
Not in this case. We took an off-the-shelf, I think, VGG or ResNet. We played with a few that was pre-trained on ImageNet. I know another popular thing is now to pre-train on X-ray images themselves. I think I've seen some improvement in that case. Mm-hmm. But we'd like to have it so that you can just use an off-the-shelf type of CNN. So the engine in the driving this thing can be very easily utilized.
Well, thank you again, Evan. Let's give him a round of applause from Philips.